So yes, my screen is shared. Yeah, thanks for the great introduction and great to be here. And hopefully I'll be able to learn you some new stuff. So first of all, what I'm going to talk about. So I'm not going to talk about very specific use cases. I'm just going to talk about what you can use automated ML for and what are some of the pitfalls I see when applying it in practice. Yes, so first of all, why automated ML? I mean, because it's fun and to learn, but also why are people paying for it? So first of all, we see that the number of use cases for ML is really growing fast. However, number of ML engineers is going slower. This is, of course, one hand for ML engineers, this is a good sign. So there's lots of jobs available, good for salaries, etc. However, for people wanting to apply ML, this is a bad case. There's a third reason is that ML engineers typically lack the domain knowledge. They're experts in one thing, and that means you cannot be an expert in another thing. So what that means is that to keep up, we need more people who can build advanced ML models, and we need to enable people to build them faster. And this is automated ML. This is the promise of automated ML. Build models faster and have more people who are not experts also build them. So this is, of course, not, this is part of a big spectrum. So you can go from build your own chip, which I was involved in a very small bit some time ago. This is really advanced, and this is what people used to do 60 years ago when they wanted to do software engineering, right? You first build your own chip. We don't do that anymore. Well, people do, but other people. Or at the other end of the spectrum, you have, well, something like Jarvis in Iron Man. Computer, build me a robot. And the computer will go ahead and figure out what to do. Of course, we're not there yet. So where we are currently, I mean, if you look at TensorFlow, PyTorch, these things already make it enormously easier. When I was starting out with machine learning, we had to write our own automatic differentiation libraries in NumPy, or people before that were doing it in C, or maybe even in assembly way before. Trust me, you don't want to do that anymore. Of course, for fun, but not for a job. So what I will focus on today is this small part, which I think we now call automated ML, which is hyperparameter optimization, low-code ML, and end-to-end automated ML. And hopefully, well, I'll get to the end. So automatic hyperparameter optimization. I'm going to assume that everybody knows what the hyperparameter optimization is, but well, hyperparameters are these things that are that sort of describe how the algorithm should function. So you have an algorithm, let's say a neural net, but how many layers should it have? What is the learning rate of your optimizer? Which optimizers should you have? That sort of thing, which these are the things I call hyperparameters. Instead of the parameters, which are the weights of the neural network that you do with training. So the automatic hyperparameter optimization is sort of the next step from, well, manual, people figuring out somehow which numbers to put in, and then have some intuition and try it, and then build your intuition. Of course, this works, but it's not very scalable. So people started developing grid search, which is very easy to set up. You just go, you set all your hyperparameters, and you do just a grid search. You go this direction, and you go this direction, and then you go whoop, 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 whoop. However, if you have 10 dimensions, even if you want, it scales. So if you want 5 points in each dimension, you have 5 to the 10 number of hyperparameters you have to check, which is impossible, of course, unless you're Google, well, even then. So people came up with random search, which was supposed to be better than grid search. So the idea is that some hyperparameters are not so important and some are more important. So random search wasn't, well, it's not biased, at least. So this was proposed, I think, well, before 2012, but really popularized by this 2012 paper. Well, actually, this is something that we could try to optimize, right? We could machine learning help us further machine learning. That's the idea, right? Machine learning should help us automate task that computers are better at. So why not a machine learning algorithm? And this is called automatic hyperparameter optimization. So what we want to do is we want to fit a function to this landscape of the hyperparameters and find the optimal point where the training algorithm performs best. So the problem is these individual points, these are the outcomes of a full training of a machine learning algorithm. If typically this can take hours or days or well, sometimes when you hear about these large language models, these GPTs, these can take months to train on supercomputers. So you don't want to do that too often, right? So the idea here is that people fit, they use a Bayesian method. So they fit a non-parametric model, and they update where you should look next to optimize the number of points that you want to minimize the number of points before you find your minimum. So here is an example of how this works. So the algorithm takes a few points and then it builds a model, and then the next point it takes, so it wants to maximize, it goes to the point where the 95 confidence interval is the highest, and then it says, okay, I want to calculate this point, and then it reduces the uncertainty at that point, and then slowly it converges to the maximum point. And so this is two parts. So one, it fits a model, and secondly, it finds the next point in your target space to optimally find your best point. Right. So I wouldn't advise to try this just for yourself. You could do it if you want to learn exactly how to do it, but this search space is quite complicated, right? So you have continuous parameters like the learning rate or the dropout rate of your individual layers. You have discrete parameters, how many layers, for example, the kernel size of your layers, if you have a convolutional neural network, the number of hidden units per neural network layer. And you even have unordered parameters where, okay, let's say you want to try Adam versus SG, stochastic gradient descent versus Erasmus problem. So you don't know how to order these. So this method should work with all of these. So several general methods actually exist. So these are Gaussian processes are used sometimes. I think they're not so popular anymore for hyperparameter optimization. You have hyperband, which is based on reinforcement learning for bandits, they're called. So these old slot machines. And the one of the most popular right now, I think for actual hyperparameter optimization is tree structured Parson estimator, so typically abbreviated as TP, which was actually introduced by the same people who popularized random search, and even before they introduced random search. And there's a whole bunch of free libraries that exist for this. So I'm mentioning a few here: Scikit, HyperOpt, Keras Tuner, Optuna, HyperOpt, but there's a lot more of them. And the great thing is that they're open source, they're free, they're compatible with almost all the machine learning frameworks, and they work for any kind of machine learning algorithm, really. Any machine learning algorithm where you have to apply, where you have hyperparameters, you can apply them. And they're really simple to code, actually. So you just, I'll show an example below. But you have to just specify which hyperparameters you want to tune, what are the limits, and what is the type. So is it discrete, is it continuous? What is the typical space it lives on? So learning rate, for example, is typically on a log space. So you don't want to just go between 0 and 1 uniformly, but let's say 1e minus 10 to 1e minus 2, and then say, okay, it should be log continuous, log uniform. You select if the method library you have, you select the method of optimization, you select a metric to optimize. You have to code that typically, and typically I would say a validation loss or validation accuracy using cross-validation, and specify how long you want to algorithm to run. And this is really, I mean, this is MNIST with hyperparameter tuning. So it's really like 5 lines of code. So here you see, yes, here you see the number of hidden units. So this is Optuna, which I'm really a fan of. So you say just suggest an integer between 2 and 128, suggest the dropout rate, and then train 10 times. And I want to optimize on validation accuracy at the end. And then it starts running. Yeah, it's really simple to code. And you can say, okay, maybe I also want to choose my activation function. I want to optimize my learning rate. You can also, you can do that. So what are the issues? What are the problems with this? It's as Uli also already was saying, it's very computationally expensive typically. Here it's doable, but you see, so I have a pretty beefy computer, and it takes, with this very simple model, it takes just a few seconds. But imagine you have a model that you want to train, that needs to train for 10 minutes already, which is pretty fast. But now you have, let's say, 16 hyperparameters, so you want to have a fair number of trials. You're looking at a big computation exercise. Related is that these methods are typically very difficult to parallelize correctly. There are some possibilities for this, but yeah, it drops in performance. There's some way to do this, so it's yeah, you can prune trials. So the these libraries have options to prune the trials if the start is unpromising. Of course, there's a risk that right, this trial might drop very low after 20 epochs. You don't know that. So yeah, it's a bit of a problem. But I think typically it's worth it. One other issue is that because you're reusing your validation set a lot here, and it actually will overfit on the validation set if you're not careful. So you have to have a separate test set, and maybe even another one if you're going to compare different runs. Also, there's a lot of random numbers, random starts involved, so it can be hard to make reproducible. But it's, yeah, minor item, I would say. Still, I would say this is almost always a win over grid or random search. And it's very easy to implement. So if you have the data, if you have the computing time, always use automatic hyperparameter optimization. Always. Yeah. And it's also typically worthwhile to look a bit at what your algorithm is doing in the meantime. So this is from Optuna, which has this pairwise, so you can see which hyperparameters are correlated to each other and which are, so where are your optimal points going. So for example, I would say the hidden units, it's clamping a bit. So maybe it makes sense to increase the number of hidden units in your search space. And here it says, well, dropout rate, yeah, maybe the lower values are more worthwhile. Remember, it will try to find the worthwhile region, so it will find more. It will find more points here. It means probably this region is better. And for example, learning rate, well, it doesn't seem to matter that much, which is a bit strange, but maybe that's within this range. That's true. So always look at this sort of graph while you're optimizing. In the interest of time, I will skip this because I will go into conclusions. But yeah, I think this is one of the yeah. Otherwise, I will run out of time. So going on to the next step. I mean, the hyperparameters optimization is nice, but it has this drawback of very computationally expensive, and still you need to do a lot of coding. Can we do it on a higher level than before? So can we do automatic feature engineering? Can we optimize our search parameter space, as Uli was telling? And can we do a neural architecture search, which is more efficient than the brute force search? So this is closer to the idealized picture of ML. So data plus labels, put it in a big algorithm and deploy, right? This is the cartoon picture of ML. Unfortunately, if you ever deployed or tried to deploy a machine learning algorithm in practice, this typically involves 15 steps and a lot of human interaction. Yeah. So can we go closer to this ideal depiction? So end-to-end automated ML, this promises. So it has automatic hyperparameter tuning, automatic feature engineering, advanced neural architecture search, and actually it makes it work by using some meta learning. So it uses the knowledge of other similar machine learning problems to accelerate the search. And well, this sounds very fancy, but really the nuts and bolts of this is a clever combination of, so you have algorithm selection based on past results, and you try on a sub-selection of the data. There's a lot of transfer learning involved. So you have a lot of pre-trained networks on slightly different but related problem sets to start off from. And you use reinforcement learning or genetic algorithms to select new possibilities for networks and hyperparameters. And this together is the promise that this will bring us to the fully automated ML. And make no mistake, this is really big business. So every big company that is offering machine learning platforms is offering AutoML. There's also some open source variants. So AutoWeka or its successor AutoScaLearn and Ludwig, actually developed by Uber, are open source, and these others are all commercial offerings, and they really put a lot of effort, engineering effort, and a really lot of marketing into it. So it's really there's. I'm not going to be able to discuss their advantages or disadvantages. It's just there's too many of them. It's really big business. There's of course the risk. So the promise is that you don't need an expert anymore, right? So you just you give it the data and the labels, and out comes a fully performant model that just works, right? But of course, if it works, you don't know why, and if it doesn't work, if you're not an expert, how are you going to fix it? It's like this cartoon is very, very AutoML, right? This is, you just pour the data in and we stir the pile until they start looking right. Of course, this is not how it works in practice. So you need an expert to diagnose and fix problems. Actually, you would prefer an expert who can spot the problems before they occur, right? So I'm going to do one example of where this goes wrong with something not AutoML, but AutoML related. So this is the risk of using a pre-trained network. So we had a few weeks ago, maybe months already, so somebody made an upsampling neural network and based it on StyleGAN, a neural network open source by NVIDIA. So you can have the Doom guy from the classic video game Doom, and it becomes, sort of realistic human face. So very nice, very nice. And so people started applying it to different faces. And one face which was often used was this face. So you have a pixelated version of Barack Obama, and it becomes a white person. So using this pre-trained network gave us a very biased answer. So this problem occurred because StyleGAN was trained using a dataset of mostly white faces, and there were some problems with the cost function. And also, I learned. So the thing is, if you just blindly apply this AutoML, you're using these pre-trained networks under the hood. That's just how it works. Otherwise, you'll not be computationally effective. And this means that you have to look out for this kind of results, because these networks, which are, they're not bad. They're state of the art. These StyleGAN, this is not something an amateur made. This is NVIDIA with hundreds of machine learning engineers, I think, and using an enormous amount of compute and data. They make this network, and then you apply it in a certain way, and you get this. So you really have to watch out how you apply these networks, and also if you're not, I'm going to skip this. So you still need machine learning experts to debug this and to fix it when it goes wrong. If you don't, you're not going to, I mean, NVIDIA is not going to fix this for you. Also, I mean, if it doesn't work, so AutoML is not 100% guarantee. It does work, right? It is not magic. So what is holding back this performance? Is it the amount of data? Is it the quality of the data? Is it the algorithms? Should you use different algorithms? AutoML will not tell you what is the problem, right? It will just tell you, okay, this is the best I can do. Also, yeah, you still need to interpret your outcome results. You still need somebody with statistic knowledge to see if this is significant, or is it just random choice, or even worse. So the main problems of machine learning, I would say, is not the algorithm, the implementation of the algorithm. And this means that you will still have the problems of, well, identifying the right data questions to answer with the data. This is something that AutoML will not do for you. You have to have an expert here. How to avoid overfitting, how to avoid this bias that I gave an example of. This is really, these are the key questions. And this is where the experts, even if you have a very fancy AutoML system, you still need experts to do this. Debug, get the best results out, you'll need the experts. What are the advantages, though? There's also, I was a bit negative on automated ML, but actually I think it's a big opportunity. So you can spend more time on the important questions. So which data do you need for this problem? Which problem actually will this solve? Is this a problem that we need to solve? That sort of questions you have more time for. Also, how will you deploy your model? This sort of thing is very, this is overlooked. Typically, you're happy if you have a model to deploy, and then you start thinking, what will actually, how will I do this? It also makes the a democratization. So you take advantage of these huge compute resources that these big vendors did for you to make the meta learning work, and you can iterate much faster, and so you can explore more options. There's a short note on these commercial frameworks. You have to think about, can you deploy it everywhere you want? Who owns the data? Who owns the model? Who gets the blame if it goes wrong? And typically they're a bit behind in the state of the art, but that's, yeah, you'll find that out. So for me, I think AutoML is the future. Yes, it will take over some of the work that ML engineers currently do, but there's new opportunities. Secondly, we needed to make the expected growth in ML possible. And third, I think we will have more demand for ML engineers in the end. Yes, so this is my main message. Thank you, and I hope you found it interesting.
Thank you so much, Jan. I think this has been a brilliant one, and especially understanding, right from, hyperparameter optimization to AutoML and the details of it, and how beginners can look at AutoML, and why there is going to be always a need of experts and engineers in this area. And even though AutoML is reducing the time that we take to implement, machine learning, but expertise, because of the shortcomings of AutoML, will never go away, and how it can be put into practice rather than just being into theory. I think that has been the brilliant thing that this talk has brought to. So I'm really thankful to you, Jan, and I hope everybody has enjoyed this talk, and it has a lot of learning for them to take away.